Hello and welcome to the module 1 part B of this neural networks for computer vision and natural language processing course. The topic of today's lecture is supervised learning. In this lecture, first we are going to introduce the supervised learning. Then we discuss linear regression algorithm under supervised paradigm. First, we went for training of the linear regression, where we discussed about hypothesis function and the cost function. Okay, we'll start with supervised learning. As we discussed earlier, supervised learning is two main variants. One is regression, another is classification. In regression, the labels are from continuous valued. Actually, what does this mean? We introduce one term here that is called label space, this C. For regression, this C is continuous valued. That means it takes any real values. So, this C is a real space for case of regression. Whereas for classification, this C is discrete valued. So, it is from discrete space. But what does this mean? Classification may be a binary classification, may be a multi-class classification. For binary classification, example is classified as true or false, or positive or negative, either 0 or 1 or plus 1 or minus 1. So, these are the two class and it is a discrete values. In multi-class classification, also more than two classes, maybe 1 to 2 up to k classes where k is equal to 2, but this is the discrete valued classes. So, in supervised learning, there is two main variants, regression where this label space is from real space and the classification where the label space is from discrete space. Next, we try to understand bit visually that what do you mean by regression and the classification. Now, in regression, as you know, that there is some label sample, since it is a supervised learning, is given. So, this is a paired sample, the xy pair. For x value, there is a y value is given. By virtue of these values, we want to hypothesize a particular curve. For this example, it is a line. That means it's a linear regression, it may be any curve. So, for this particular example, we predict some values that may be a temperature or a height of a person. Given this example, we try to find this line so that for any values in x-axis we can get the corresponding y values. In case of classification, there is a two group of data. Basically, this is a binary classification and it is annotated or labeled such a way this is a plus or this minus. So, here our task is to find out this separator so that any new instance is coming can say that okay, it is some positive values or plus something like that, so that we can put it here or it is. So, based on this separator, we can take the decision it is either in this class, plus class or in minus class. For example, the spam filtering, email may be spam or not spam. So, it is a plus 1 case or a minus 1. The multi-class classification, this has just been extended for multiple classes. This is a cross, the green cross, the blue dash and these classes. Now, this class, so we can take this that for example, that face classification, a person can be exactly one of k identities. So, these are the example of the multi-class classification. In supervised learning, as we said earlier, there is a training data. In supervised setup, this training data is coming in pair. This pair x and y. X is a data instance and y is its label. Now, this x may be d-dimensional data. So x belongs to this d-dimensional data, the input instance, and y is level. So if you write bit mathematically, you can say this is x1, y1. x1 is basically a vector of which a d-dimensional vector, and x2, y2, and dot dot to xm, ym. This m is the number of data samples. So this is coming from the d-dimensional space from x and the level space. This y is from space. Now if we can understand specifically, this R of t is the d-dimensional feature space, xi is the input vector of the ith sample, yi is the level of the ith sample, and c is the level space. It can be visualized with these values. Okay. Now the question is that these particular dots, these blue dots, is this given training data. Okay. So if you can say this is a x1 and this corresponding y1. For this particular example, x1 is a single dimensional. So you can see that this kind of data points have been given. Now there is a situation when a new data come means that we get the x values. Can we predict the y values? That is the main agenda of this supervised learning. So for that reason, what we required, we have to hypothesize a function that represents this data, these blue dots. Okay? So that if we can get some curve, it may be linear, maybe non-linear, then for any x we can get a corresponding y, and that is actually our intention. So this is the data points xi, yi are drawn from some unknown distribution. This is important because the data points have been given, but the underlying distribution of the input data samples or labeled data samples are not known to us. So what is our purpose here? That we would like to learn a function h such that this function h is represent these data points very well. So when a new pair, that the x is coming, we have to say that h of x is y. That means this thing we can predict, okay, that with a very high probability. So this is the ultimate agenda, ultimate purpose of this regression problem. Okay. Now let's try to understand that this is in bit in depth. Now as we have discussed, there is some data points have been given, and the function that we want to learn, that exact function that these data points are belongs to. But is it possible to find such function entirely? It's impossible task, because that if we have to find the exact function, then we have to know the every points. Let's say, and every point is infinite number of points. So we don't get the exact function. But what we can get, given a set of examples of these examples, a function that we can get that approximate this function. So we hypothesize a function that is going to approximate f, and that is this h function. This is called hypothesis function that is going to approximate f. And how we get this h? By virtue of these data points. So the main agenda is that to find a hypothesis function h such that h is very well approximate this f, giving a training set of examples. This is the main issue or main agent of the regression. And since the nature of this hypothesis function is linear in this example, we can say it is a linear regression. It's a very straightforward process, very simplified process, because it is not require any prior knowledge, and these examples have been given. So essentially what is important here is that we have to approximate, or we have to hypothesize a function h which approximates this target function f given these data points. Now take a example. Now these are the data points that we can get this hypothesis function of different kind. Our ultimate purpose is that we're going to find a hypothesis function, maybe linear, maybe non-linear, this curve, and a very complicated curve. Okay, but it every time our basic purpose that it essentially represent the data points very well. Now you can see your first, it is a linear regression, and this is a linear or is a straight line, and it will represent the most of the data points. Now again it's a curve. This is much more accurate, that represent data point. But one thing we trying to understand here, the complexity of a straight line and complexity of this curve is different. The complexity of the curve, or you can say the basic, what is the how to represent the curve, this mathematical equation is complicated than the straight line. Again we can go for another very complicated thing. Okay, so that is also, that is we'll say in next in our successive discussion, we say this is called model complexity. So there is a open tracer called, we always prefer a simplest hypothesis consisted of the data. Now what we're going to understand, that the linear regression. So whatever we have seen in our last few slides, that in regression problem these data points are being given. The data points are what? These are the annotated, or it is a labeled sample, so paired sample x and y, and this is the data point. Now how actually it is being given? This is a kind of x1 y1 or xy pair. Since x is univariate in our example, so x1 corresponding this level, x2 corresponding its level, and so on up to m, where m is the number of training examples. These are the examples. Maybe x is a study hours per day and y is the example, and such and such things. So here m is number of training examples, x is input variable or feature, and y is the output or target variable. Okay. Now what is the task of the linear regression? We have to find a straight line. Why straight line? Because our is a linear, and it is a kind of single variate linear regression. So a straight line, we have to find a straight line which is consistent. That means the straight line is a well representation of these data points with these level samples, such that for any new x is coming, then we can get the corresponding y value. That is very important, that we have given these data points. By virtue of these data points, or by utilizing these data points, we hypothesize a straight line here, so that in any x that is not given in these leveled samples, you can get the corresponding y. and that is the main purpose of this. So finding this hypothesis function is our main agenda in linear regression, and for this particular case we find a straight line. In linear regression, as we have seen before, that a training set, that is the example data set, is used to train the machine learning model by finding the optimal parameters of the hypothesis function. Now, what do you mean by training data set? We have seen that this is a paired data, there is input output pairs, x1 y1, x2 y2, xm. So this is the m number training samples. Now, what we have to do? We have to hypothesize a particular function. That function is going to represent this data point very well. That is our goal. Now, we have given a training set, and this is basically a labeled training set. Okay, so we have to find this hypothesis function. So what do you mean by finding hypothesis function? Since it is a parametric function and this 50, 51 the parameters, we have to finding the hypothesis function means we have to know the parameters. So essentially from these data samples we are going to understand or going to know what are the parameters of this hypothesis function. Okay, so that is the one of the major agenda of this linear regression problem. Now, what is our goal? Build the parametric hypothesis function h5x and find out those 50 and 51 that best fit the data. And that is very important, that best fit the data. As we have seen in the last example, that given this data points, we have to find a hypothesis function. In this example, it is a straight line that is best represent the data points. Okay, so how we can get this best line or straight line? That we have to minimize the prediction error so that this prediction h of xi is very close to the target for all training examples. So one example you can say what we have taken in the last slide. These are the x and y pair. This is x is univariate and y is its levels. Then is the value x value y value pairs. So and such m training examples have been given. Okay. Now, when we are trying to find out this hypothesis function for a particular straight line, to find how, if we change this 5051, how this straight line will change. Let's take some example to understand this. This 50 is 2.5, but 51, this slope is 0. So it is essentially a flat line. So if the prediction doesn't change regardless of the x value, so it's just a flat line. Now, if there is some slope, so this particular line is the corresponding h of x, and this slope is 0.5, but intercept is 0, so it is just going through the origin. Now, if we increase the intercept, that is 1, so that is going through this 0.01. So what we can understand, by taking the different values of these parameters 5051, we can get a different kinds of lines. And what we really want to do, that we have to find out such line that is best represent the data points, the example data points. Okay, so with this background, now we define our problem of univariate linear regression. Why it is called univariate? Because this is the x values is single dimension. So linear regression with one independent variable x and one independent variable y. So given x, we have to find the y. And the examples are being given in that format. in xy format, as you have seen in last slide. So in this hypothesis function, as we have defined earlier, that h phi x is equal to phi 0 plus phi 1 x, where phi 1 is the parameters. This function is basically a straight line because it is very similar to this y is equal to mx, where phi 0 is equal to c, phi 1 is equal to mn. So the hypothesis function h phi x, what essentially this function do? It basically works as a mapper or as a mapping function between x to y. So it maps the input instance to the corresponding levels. So this input instance corresponding given x. So the basic agenda is that by virtue of these points, these data points, or utilizing these data points, can I find some line? So that if we get the line that any x value, what is not given in the training sample, we can get the cost of y1, and that is our main target. The goal is to find this phi 0 phi 1 so that we can find a line that best represents the sample data points, and that is very important. Not any straight line. What straight line that best represents the data point? Okay. So if we get this data, as we said, that any x we can get the corresponding new x not given in the data samples can get the corresponding y. So now the main question is how we are going to find the best line which represent these data points. To answer this question, we defined a function that is called cost function or loss function. Now, first to understand what is this. Okay. Now we can see that this is a given data points, and when we hypothesize a line, so this the corresponding to the data point, our predicted point is this. So there is some error. For every data points, there is some error. So what we required, we have to minimize all these errors. Okay. So actually our cost or loss function is essentially the summation or normalized summation of this squared error, as we have seen here. So now we defined our cost or loss function is how well the hypothesis function fits the training data. How? By measuring this squared error. So what we have done here, you can see here is h phi xi is basically our predicted this value, and what is yi? This is this value. Take the difference and make the square and sum it over all the data points. So m is total number of data sample 1 to n and normalized by this. So it is a normalized summation of the square error, and that we're going to say this is our cost function or loss function. This is g of phi 0 phi 1. It's a bivariate function. Okay. Now that function should be minimized to get the baseline. So what do you mean by this minimization? We have to find out such phi 0 phi 1 so that this j of phi 0 phi 1 should be minimized. So the basic idea or basic agenda now, choose such phi 0 phi 1, this phi x is close to y, or for our training example x y. Okay. Now why this is squared error? There is some advantage. First of this squared error is differentiable. We can use absolute function also, but it is not differentiable. Another important advantage, this particular squared term penalizes large errors more heavily than the small ones. So that is also very important. And most importantly, this cost function or loss function creates a smooth and convex function that is easy to optimize. That we will see in our slides. Okay, now with this background, try to find out the cost function for our univariate linear regression. This is univariate linear regression. This x is single variable. The cost function J5051 is a function of two parameters, phi0, that y-intercept, and phi1, the slope. And this is defined as, this is a difference of predicted value and the actual value, square it up and take the summation over the m samples, normal. Okay, now if we plot this function, we can get this kind of convex paraboloid. Okay, convex paraboloid is a bowl-shaped surface. Now if we can intersect in this way, we can get this kind of concentric parabolas or ellipse. Basically it is a concentric ellipse, and this is called contour plot. And what is our purpose? Our basic purpose is that we, for any given 5051, we are maybe anywhere in this surface. So starting from anywhere, can we get this minimum position? This is basically the global minimum. One important nature of convexity or a convex surface, error surface, that our local minima and global minima. So if we find the local minima from, that means we started from anywhere and we can reach this minimum position, then we can get this error function, this loss function or cost function be minimized. Okay, so the lowest point of this convex surface is the global minima, but the square error is minimized, indicating the best fit line. How we can do this? We can start anywhere. So it is a line, but it not essentially give a very good representation of this data point. Okay, now we go here to here. Now we can get, it is also not very good, but better than this line to represent this data point. Again we go. Now we can all very close to this our global minima. So you can see the line is very much consistent. So in this contour plot, a similar thing has happened. So this is the way we can start anywhere in this surface, this convex surface, and since it is a convex, then we can travel from here to here, here to here, maybe many other steps. We can reach this global minimum, and that is the way of finding the global minimum. And if we can global minima, we can find it is the baseline. The corresponding 5051 give you this particular 50I plus 51IX. This is the baseline. Okay. So what we have discussed this lecture, we introduced supervised learning. Specifically, we discussed the linear regression, and then how we train our linear regression model. We define hypothesis function, we define cost function. In the next module, the module 2, we'll see, we find that the way that from in this particular surface, from here we can come to here and come to here. We can find, if we can reach this global minima, we can get the baseline. But the question comes, how to find the global minima in the error surface, starting anywhere. For that, we need an algorithm. It's called gradient descent, which is the topic of our next lecture. Thank you.